So what we're going to do now is actually a review of some stuff that you saw in your statics or mechanics classes, and we're going to talk about beam theory. So what is a beam? A beam is a structural member supporting loads at various points along the member. So the transverse loads of a beam are classified as either a concentrated load or a distributed load. So if you remember from class, you'd have a concentrated load, you would have a distributed load, and in statics mechanics, you would take the distributed load, find what the concentrated load is, and locate the force. And so why do we care about all this? Well, this is going to cause bending within the beam. And so we're going to end up having an internal shear force and an internal bending moment that will be inside the beam that will be calculating out bending stresses on. So as long as they have perpendicular loads to the longitudinal axis, we are going to be dealing with them and calling them a beam. Now, beams are classified in two broad examples, two broad ways, and it's all depending on how they're loaded. And the first is what we call statically determinate beams. So just like every other thing that we've done with the class so far, statically determinate means that we can solve all of the external reaction forces using statics, using that sum of the forces in the x direction, some of the y, some of the z, some of the moments about x, y, z. We can solve that just purely on statics. And so the other type of beam would be what do we call this? Statically indeterminate beams. So statically indeterminate beams would have a redundant force, a force that is not needed. We cannot use statics to solve these because we need more information. So what ends up happening when we have a statically indeterminate beam? How do we solve for those external forces? We do it in the same way that we've done with our other statically indeterminate cases that we've seen during this class. We have to spool up another equation, some kind of kinematic equation where we know something about the deflection or the slope of the beam. Now, we'll talk about all of that later, much later in the class when we do our equations of the elastic curve. This will come into play. But what we're going to do in this next couple of lectures is basically we're going to review how to make shear and moment diagrams. Because if we have a shear and moment diagram, we can take a look at the beam at any point and use either that shear force to calculate out shear stress, we can use that moment to calculate out bending moments. And so to properly design a beam, we have to know how these variations in shear and bending moments interact so we can identify the maximum points. Because that's what we care most about, is where do we have the maximum bending moment, because at the maximum bending moment we'll have the maximum stress. How do we identify where the maximum shear stress is, because that will give, shear force is, because that's where we'll have the maximum shear stress. And that's really what it's going to come down to. I'm going to show you how to calculate it through the entire beam at any point, but what's going to come down to, the important part, is going to be where is the maximum.